Now that we've uploaded all the components, what we're going to do next is identify what are the effects and what are the safety measures that we already have. Once we've done this, then we can generate the FMEDA table. So in order to generate the effects, this can be done in a couple of ways. One, it can be manually added. Two, it can be uploaded from an image. Or three, it can be available, it can be uploaded from an FMEA. And once the HARA feature is available, it can be uploaded from HARA. Why this is important is for each hazard, we want to be able to perform the FMEA. For now, we're just going to take a simple example. We're going to manually add one. We're going to call it effect 1 too high sensor value identifier. And as far as safety mechanisms go, same thing can be added from, can be manually added, can be added from image. We're going to take a simple example. We're going to add them manually. We're going to add two mechanisms over here. SM1, which is a ADC startup test, which is during startup, you give a known analog voltage and you see what the digital value is. And I'm going to add one more, which is SM2. This is a watchdog test. This has to be performed by the microcontroller or the microprocessor which is controlling the ADC. It cannot be done by the ADC itself. So now that we have the effects and the measures, what we can do is we can go to generating form sheet. The form sheet is generated. By default, all these components are available. I'm going to walk through what each of this means. Now, to start off, I'm just going to click on collapse all. So what we already see is these are the components. Each component has its bit rate, and there is some additional information about the component, which talks about what is the type of component, what is the subtype. If we expand one, then we see it has two failure modes. Failure mode 1 is too high voltage and its distribution is 50%. Failure mode 2 is too low voltage and its distribution is 50%. Let's go one level below that. Let's see what metadata do we have for each of this. We start off, we have an ID. Then we have a component failure rate, which is the failure rate of the component in FIT, which is 5 into 10 to the power minus 9. Then we have the failure mode distribution, which is 50% or 0.5. Why this is important is to calculate the failure rate for this particular failure mode, which is 2.5%. Then we have the system effect, which is too high sensor value identified. Now it's up to the user to decide whether this failure mode can lead to this effect. So we have the failure mode which is too high voltage. We know if there's too high voltage, then it'll be too high. If the input analog voltage is too high, then the ADC values would be too high. That can lead to a too high sensor value. So definitely this is a problem. Now we need to talk about what safety mechanism can prevent this. Let us for the time being assume that we can do an ADC startup test to prevent this. There's other ways of going about it. You could do sensor plausibilization, do other things. But for now, let's take an example of the ADC startup test as the safety mechanism. Let's assume that the safety measure has a diagnostic coverage of 99%. This is something that can be easily modified. So we can choose whether it's high, medium, low. You could say it's medium coverage and it's 90%. The ISO 26262 has a cheat sheet that talks about how to identify what the residual coverage is. Then we need to find out the residual failure rate. The residual failure rate is what is the portion of failure that cannot be detected by the safety mechanism. What that means is the probability of this failure mode is 2.58. It's 90% covered, which means 10% is not covered. 10% will go undetected. So 10% of 2.5 is 0.25. Then we need to talk about what is can this lead to a latent safety goal violation? And assuming the answer is yes, we have to identify what is the safety mechanism for this. And let us for time being assume that this is a watchdog test which is performed by the microprocessor, the microcontroller. That is the latent safety mechanism. And for now we can assume, let's say, the coverage is, let's say, 90%. Then latent failure rate. Latent failure rate is, as you can see the formula here, is the fit times the distribution times the residual coverage into 1 minus latent coverage. And if you click over this button over here, it gives you how this is being calculated, and this is how we end up this way. Then we have another thing that is calculated, which is DPF detected. DPF detected is basically what percentage of the overall failure rate is detected by the safety mechanism and is a candidate for dual point failure. This is eventually going to be used in the PMHF calculation. So then once we have all this, we can check what the status is. We can say, let's say we can put it in review and ask somebody for a review. And once completed, we can set this to complete. Similarly, we can do this for all the components and all the failure modes. So by now, go to expand all. It shows all the information for all these components. And it's up to the user to check whether the information is correct or not. But see, notice already that most of the information is already populated. Once all of this information is populated, then we can go and look at the